So I'm giving an introduction to time series econometrics. Some of the basic concepts I will explain here. And then in the afternoon workshop session, we will do some practicals. Now, initially I shall give you some essential readings on time series. The first one that I like most is Applied Econometric Time Series by Walter Endes. This is a very good book, and an Indian edition is available in the market. There are some equations, but you have to stand with those equations. But otherwise, this is a very good textbook. Then Hamilton's time series analysis is fully mathematical. So if you are mathematically inclined, you can have this book. But the language of this book is very interesting, unlike Walter Endes. Walter Endes I found a little boring with regard to language. Then David Henry, I told you about Henry of London School of Economics earlier. He has a book, Dynamic Econometrics. This also is a little mathematical. Then for the classical time series analysis, the best book is by Makridakis and Pace. Wheelwright and Maggie. Forecasting methods and applications. This is a big book, but very simply explained everything with the illustrations. A lot of examples are given. This is the best book for ARIMA modeling. The theory of ARIMA modeling. Of course, there are a large number of books in the market. For example, I have shown the financial econometrics books. So all those books are dealing with the time series analysis. Now I have two working papers, serious working papers. One already I told you about the tradition is questioned. Then there is another one, a contribution to peak load pricing. So in both the papers, I'm dealing with the certain time series concepts. Now, I shall start with the time series process. Now, see, the time series econometrics is a little more mathematical. We will have a lot of equations and other things. So some equations we have to put up with. So I will be giving some equations. So I shall explain everything, and some very new concepts will be there. Maybe some of you are already familiar with the time series econometrics, but otherwise for the beginnings, we will have a little more concepts to understand. So time series is a stochastic process. A stochastic process is a sequence of a random variable ordered in time. Ordered in time means, or this is a collection of random variables that are ordered in time. Ordered in time means we have, say for example, yt, that is the present time, yt minus 1. Last period, yt minus 2, the previous period of that. Then yt minus 3, yt minus 4, and so on. It will go back up to the last or the initial value yo. So when we collect all this in this order, then that is a stochastic process. Such a stochastic process is a time series process, or simply time series. So a time series is a stochastic process or a random process, collection of random variables which are ordered in time. So we know a random variable takes values in a certain range with the probabilities specified by a probability density function. That we already know. Now this stochastic process is generally called data generating process in time series econometrics. And this is the same as our population in statistics. So the population in statistics becomes a data generating process, which is a stochastic process in time series analysis. So whenever we say data generating process, remember this is nothing but the population of the time series. Now the time series data is a particular realized section, that is sample. So if we have a time series data, that is a sample from the population. That is the data generating process. Now these are the notations that we use in time series. A time series variable yt, we give a time series variable we give in terms of yt, which is a random variable y at period 2. Now, a time series, as I told you earlier, is a collection of random variables ordered in time, so that this collection of random variables ordered in time by t, by t minus 1, by t minus 2, and so on, the initial value by o. So this constitutes a time series process. From the time series process, if we get a sample, then we have simply a time series. Now the capital T is the standard number of observations in a time series. In a cross section, we use capital N or simply small n, and here we use capital T for the sample size. So here we have a time series. For example, this is the per capita net state domestic product of Kerala at constant prices. So we know it is arranged in order of 10. And this shows the graph of this per capita net state domestic product. And here we have the wholesale price index for all commodities in Kerala for certain months. I haven't given the full data. I have given the starting point 71, 72, this monthly data up to 87, 88. This is the graph of that data. Now, I shall give you, it is not given, I shall give you a brief history of time series analysis. Time series was initially conceived by a statistician in the 18th, 19th century called Fourier. And he postulated that any time series can be approximated using trigonometric function. That is using the combination of sine and cos functions, we can generate time series data, so that the time series data can be approximated as the combination of trigonometric functions. Any trigonometric functions, but it should be a combination. For example, combination of sine and cos the variable, or sine and say tan, and so on. Then, in the beginning of the 20th century, that is 1926, a British statistician called George Yule argued that any time series can be approximated in terms of a autoregressive process. And autoregression, we know, is a function of a variable in terms of its own past values. For example, yt as a function of its own past values, by t minus 1, by t minus 2, and so on. So any time series, according to Yule, can be approximated in terms of an AR process. Then, after nearly 10 years, in 1936, a Russian statistician, very famous Russian statistician, Slutsky, formulated that a time series can be approximated as a moving average process. A moving average process as I already told you, is a function of a variable in terms of a random variable and its own past values. That is yt in terms of, say, epsilon t, which is a random variable, and its past values, epsilon t and epsilon t minus 1, epsilon t minus 2, and so on. So that is a moving average process. Then after about 20 years, around 1956, a Swiss mathematician, very famous mathematician, Hermann Wald, combined AR and MA process, and we have a theorem by him in terms of a decomposition theorem. And that decomposition theorem combines AR and MA process, and thus we have a new model, that is ARMA, autoregressive moving average process. So here I am giving the AR1 process of yt as a function of its own past value yt minus 1. B is said to be the auto-regression coefficient. And MA1 process, as I told you, is expressing a variable in terms of a random variable ut and its lagged value. Here we have an MA1 process because we are using only one lag. Here also we are using one lag. Therefore, we have an AR1 process. Now comparing these two, AR1 and MA1, we get an ARMA1 process. That is yt equals a plus b by t minus 1 plus ut plus d ut minus 1. So in this case, we have the lagged value of the dependent variable and the present value of a random variable ut and its own past values for an ARMA process. Now, what is actually this time series?
Sir,
Okay.
here, yes, sir. Sir, here actually AR1 and MA1 process is almost similar, just a additional intercept is considered in AR1 process, isn't that?
No. They are not the same. They are not the same. In an AR1 process, see the dependent variable is yt. And as an independent variable, we are giving its own past value yt minus 1 and a random variable ut. And we have an intercept here. We can have an intercept here also. Usually it is not explicitly written. But in MA process, the dependent variable depends on the random variable ut and its past value, ut and ut minus 1. So there is a difference, vast difference. What idea?
Sir, ut is a random variable.
Yeah.
Or
It
the
is a
random error term actually.
Which one? Random
Sir,
error
it is
thing, right? Random error
random error
thing,
term
right?
and its lag values.
And its
Lag values.
previous value. Previous
Yes.
value, right? Yeah.
Okay.
That is MM process.
Okay, sir.
Okay.
Okay,
Yeah.
sir.
So when we combine this, we get this one. Here we have the lagged value of the dependent variable, and in an ARMA process, we have the lagged value of the dependent variable and present and the lagged values of the random error key. So that is this. Now, as I told you, behind time series, there is some mathematics. Because the AR process, the autoregressive process comes in terms of a mathematical equation. So that is why I have written time series is a stochastic difference equation. Difference equations, that particular branch of mathematics is the mathematics of dynamics. I have written here economic dynamics because it is not only used in economics, in general mathematics, we use that. So here the difference equation deal with the time as a discrete variable. If we consider time as a continuous variable, then instead of difference equations, we will have what is called differential equations. So these two are mathematical tools, differential equations and difference equations. In time series analysis, we are considering the difference equations only. So here the time is a discrete variable in the sense that it can be written as t minus 1, t minus 2, t minus 3 and so on, or simply t equals 0, 1, 2, 3, 4 and so on. Now the difference equation gives the value of a variable as a function of its own lagged values, time and other variables. For example, when we write yt equals byt minus 1 plus at, then we have a difference equation. Yt given in terms of its own lagged value and an intercept, which is a function of time. Or we can write this as yt minus byt minus 1 equals at. And this, since we are using only one lag, and all the terms have a power of 1. This is said to be a linear first order difference equation. So the power of yt is 1, power of yt minus 1 also is 1, at which is a function of time that also has a power 1. Therefore, this is linear. This is first order because we have one lag yt minus 1. Then this is a difference equation because this is given as this is given in terms of yt as a function of its own past value. So this is a difference equation. Now, usually for simplicity, this b is a constant and the at is taken as a variable, but it can be taken as a constant also. So that we can write this as yt minus b yt minus 1 equals a. Now, this is said to be a non-homogeneous linear first order difference equation with a constant coefficient and a constant. B is a constant coefficient. A is the constant. This is linear because yt and yt minus 1 are having a power of 1. And this is first order because we are using only one lag. And this is non-homogeneous because on the right hand side, A is not 0. If A equals 0, then we have a homogeneous difference equation, linear first order difference equation with the constant coefficient. So this is a difference equation. We will go a little detailing with this difference equation because everything in time series analysis depends on this difference equation, the properties of the difference equation. Now, if we include a random variable ut to this difference equation, mathematical difference equation, then we get a stochastic difference equation. And that stochastic difference equation is the AR1 process. This is an AR1 process. And that is a time series. So the AR1 process is nothing but a random difference equation, a stochastic difference equation. Now, UT is called in by different names. UT is an equilibrium error. It is a disturbance. But in time series analysis, it is called an innovation. Now, can you tell me why it is called an innovation? Anybody?
It contains information, sir.
Yeah, it is all. I have already given it here. See, consider this particular equation. Yt equals a plus b yt minus 1 plus ut. This yt minus 1 is already known to us. We know about the value of yt minus 1 because this is the past value of yt. So we already know, we have already information on yt minus 1. Any new information to this system comes from only ut. New information comes only from ut, and that is why it is called innovation. since it is UT is a random variable, it is an information shock. So information comes as a shock. That is why it is called information shock. Every innovation is an information shock. It is random. So in time series analysis, UT is taken as an information shock, or it is called innovation. And this innovation is assumed to be a white noise process. White noise process. Now, what is this white noise? We already know about noise. Noise is the disturbance. UT is an error term or a disturbance term or noise term. This term white noise comes from signal theory in physics. So in time series analysis, we have taken a lot of concepts from signal, especially from signal theory in physics. Now, you are already familiar with the concept of white noise because you have already familiar with the. Okay, before that, I shall show you the graph of a white noise process. This is the calculated spectrum of a generated approximation of white noise. So this one, and this is the example realization of a white noise process. Example of a realization of a white noise process. We will come back to this again. And before that, let us see the properties of a white noise process. The property of the white noise process. See, as this spectrum shows, this has a flat spectrum. This is the flat spectrum. So a flat power spectral density, that implies that the distribution of the white noise has a zero mean, a constant variance, and a zero autocovariance, which shows that there is no autocorrelation. And now you are familiar with this noise term with these properties. The last day I told you that if these three assumptions of the error term are satisfied, then the error term is called a spherical error. A spherical error. It is a spherical error. And this spherical error is the white noise in time series. So the white noise is nothing but a spherical error in time series. It has a zero mean and it has homoscedasticity, that is constant variance, and there is no autocorrelation for that. If these three assumptions are satisfied, then in time series, the error term is a white noise, and it will have a time series plot like this. Here the zero is the mean, the zero mean. Now see, can you tell me whether this white noise is stationary or not? Anybody? Just for the time being. Anybody?
Stationary, sir.
Is this a stationary process? Is
Mean
it a
reversion.
stationary process?
Mean
Yes, sir.
reverting process.
Okay, you know, okay, you know this. So we have a large number of mean reversion because whenever the time series plot goes up, it will come back to the mean and it will proceed, goes down, then it will go back to the mean, goes up, come down. So we have a large number of mean reversions. So a mean reverting process is a stationary process. So these are certain equations. As I have already told you, the white noise has zero mean, constant variance, and there is no autocorrelation. And we have another assumption about the normality, but this assumption is not very essential. If this assumption also is satisfied, then the white noise is called Gaussian white noise, because the normal distribution is called a Gaussian distribution, because the normal distribution was formulated, its originator was called Frederick Gauss. Now, as you know, white noise process is a stationary process, but not vice versa. That is, for a stationary process, mean, variance, and covariance all are constant. That means they are all independent of time. And this particular assumption of stationarity is called covariance stationarity, or second order stationarity, or weak sense stationarity, or wide sense stationarity. This is the stationarity concept that we use in time series analysis. That is, mean, variance, and covariance all are independent of time. But we can find that even though covariance is independent of time, it is a function of the lag. The lag is represented in terms of k. That is t minus 1, t minus 2, t minus 3, and so on. The k is 1, 2, 3, and so on. Or in general, t minus k. So covariance is a function of lag, but it is independent of time. Then we have a stationary process. So white noise process is a stationary process, but not the other way. That is, a stationary process need not be white noise. So what is for particular about the white noise and the difference between white noise and stationary process? For a stationary process, mean, variance, and covariance all are independent of time. They are all constant. What about the white noise process? Do you remember? For the white noise process, mean is 0. So it can be taken, so it need not be constant. Then variance is constant. Then what else? What about the covariance? Is it a constant for the white noise process? It is 0. Okay, you remember this one. See, the covariance is 0 for a white noise. It has 0 mean, constant variance, and 0 covariance. That means there is no autocorrelation. But for a time series, for a stationary time series, mean is a constant. It can be 0 also, no problem. But it is a constant generally. Variance is constant, and that is so with respect to white noise process also. But covariance is not 0 for a stationary process. It is a constant. It is not 0. So that is the difference between white noise and stationary process. So we can say that white noise process is a stationary process, but a stationary series need not be white noise, because for a stationary series, the covariance is not 0. There is autocorrelation. There is autocorrelation. So that is the difference between these two processes. So we find that yt is given in terms of the stochastic difference equation a plus b by t minus 1 plus ut, where ut is a white noise process. That doesn't mean that yt also is white noise or it is stationary. Yt may not be stationary. That depends on the magnitude of this coefficient, autoregression coefficient b. And it is b is taken as the root of a difference equation. This is the root of a difference equation. So whenever we say an AR process, then this coefficient is the root of the difference equation or the AR process. So b is the root of the AR process. Now we are going back to our difference equation yt equals b by t minus 1. Now, given a difference equation like this, we can find its solution. That solution is taken as the time path of the difference equation. That is for every time how the particular yt moves. over the time, that is given by the time path, and that is a solution of the difference equation, and that is given. This is very simple to derive, but I am not giving it. So that particular solution of this difference equation is given in terms of yt equals y o b power t. B is the root of the difference equation, b power t. Now the nature of this time path yt, whether it converges or not, as time approaches infinity, that is asymptotically, whether it converges or not, that depends upon the sign and magnitude of the root b. So the sign and magnitude of this root b determines whether the time path converges or not. If the time path converges, then we say the system is stable. If the system is stable, then in the parlance of time series, we say that the system is stationary. So that stability or the stationarity of the particular system or the equation or that particular variable depends upon whether this root converges or not. If it converges, then yt is a stationary process. If it diverges, then it is not a stationary process. So that is the importance of the root of the equation. Now, for simplicity, we assume that yo equals 1, so that we can write yt equals b power t, so that for different time periods, we can find out the time path of yt depending upon the value of b, magnitude of b, and its sign also. Now I am giving those cases. Now suppose the value of b, we are taking b greater than 1, or we are taking b is equal to 2, so that b power t we can write as 2 power t. As time changes from 0, 1, 2, 3, 4 and 5, we get the time path of yt. So 2 power t when t equals 0 is 1. 2 power t when t equals 1 is 2. Then it is 4, 8, 16, 32, and so on. What is happening here to our b power t, the time path of yt? The time path of yt, what is happening? It is increasing over the time. 1, 2, 4, 8, 16, 32, 64, and so on. It is increasing over the time. So that means it is going away from the mean 0. We have a divergence case. So if b is greater than 1, for example, if b equals 2, we have the case this. Now the other case, we are taking the value b is equal to 1, so that the yt becomes b power t, that is 1 power t. Here we have all 1. Do we have a convergence here? Is it coming back to 0? Not at all. So we have a position like this. There is no convergence. There is no convergence, but there is no divergence also. Okay, there is no divergence, but there is no convergence. Now we are taking b as less than 1, that is 0.5. So that our time path becomes initially 1, that is 0.5 raised to 0, 1. Then we have 0.5, then the square of 0.5, that is 0.25, and so on. Or in terms of 1 by 2, we have 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32, and so on. So what is happening here? We know that this is converging towards 0. So this is coming back to 0. So when when the root b is less than 1, we have a case of convergence. Now we are taking b in as minus 1 by 2, minus 0.5. In this case, what is happening? The idea is as same as the above one. We have a convergence because the absolute value is decreasing. But what is happening? Every second term is negative. So initially positive, then negative, positive, negative, positive, negative. That is, we have an oscillation. We have a fluctuation around the mean, and we have a situation like this. So the convergence, we have convergence through oscillation. We have a situation of convergence through oscillation. When does it happen? When the root is negative and less than 1. Now the other case. Now we have b, the root equal to minus 1. Here we do not have any convergence or divergence, but we have oscillation. That is, we have an oscillation like this, fluctuation like this. But there is no convergence. There is no divergence also. Now the final case, that is b is less than minus 1, or the absolute value of b is greater than 1. We are taking b as 2, so that we have minus 2t. What is happening here? We have divergence, but the divergence is through oscillation. So we have oscillatory divergence. Now let us combine all these results. Let us recap it. So we find that the first order difference equation, homogeneous difference equation, yt minus b by t minus 1, has a time part. It may be oscillatory or non-oscillatory. It may be converging or dash or diverging or explosive. What are the conditions for that? The conditions we have already seen. We found that time part yt would be oscillatory if the root is negative. That is, if we have a negative root, and non-oscillatory if we have a positive root. And the time part will be converging if the root lies between 0 and 1, or it is less than 1 in absolute term. If the root is less than 1 in absolute value, then we have convergence. And we have non-convergence because we are including the root, the case of root being equal to 1. So we have non-convergence when the absolute value of b is greater than or equal to 1. So convergence and non-convergence. So let us recap it. We have a negative root means oscillation, positive root means non-oscillation, and absolute value of the root is less than 1, we have convergence. If it is greater than or equal to 1, then we have non-convergence. So with a unit root, that is, if the root of the difference equation is equal to 1, it is called a unit root. So we find that with a unit root, there is no convergence. So that yt is unstable. The time path of yt is, the system is unstable. That instability is the non-stationarity problem. So the non-stationarity is because we do not have a convergence. We do not have a convergence because the root of the system is not less than 1. So I hope you understand that, right? So with a unit root, that is b equals 1, our first order difference equation, first order, of course, stochastic difference equation, that is our AR1 process. We can write as yt equals yt minus 1 plus ut. That means we can find out the time path of yt like ut plus ut minus 1 plus and so on. That is sum of all the past and the present random shows, summation ui. That is a cumulation of all the random shows. That is the type of yt. And this sum of all the random past shows is called a stochastic range. And that shows that the shock is persisting. That persistence of the stock is an indication of non-stationarity. So sometimes instead of non-stationarity, we also use the term persistence. That persistence means the shock is persisting over the entire time period, from past to the present. So persistence is the non-stationarity. And non-stationarity problem is because we have a unit root, or the root of the AR1 process is 1. So now with a unit root, we find that the mean of the system yt is equal to 0, but variance of yt is now, it is t times sigma mu squared. T means time. So remember for a stationary series earlier, we have seen that variance of yt is only sigma u squared. It is a constant. But with a unit root, it becomes sigma u squared multiplied by time. That means it is a function of time. So as time increases, as t increases, the variance also is increasing. Remember this particular case. Variance is a function of time. As time increases, the variance also is increasing over the time. Now, same is the case with the covariance of yt and yt plus k, or t minus k. It is also a function of time. That means the covariance also is increasing over the time. So, if we have a constant in our AR process, then we can find that the mean also is a function of time. We will get, if alpha is the constant in the AR1 process, then the mean will be equal to alpha t. That I have been given here. So this we have already seen. Now the non-stationarity can be due to two cases. One is because of the presence of an integrated process or a difference stationary process. Now see, a non-stationarity process also is called by integrated process or difference stationary process. Why it is called by these names will be clear after some time. I shall explain this later on. And this non-stationarity is due to the stochastic trend. We know the stochastic trend appears as the cumulation of all the past random shocks. That is ut minus 1, ut minus 2, and so on. All the past random shocks. That is the stochastic trend. So this can lead to a non-stationarity problem. Similarly, we have non-stationarity due to trend. Therefore, it is called a trend stationary process. Such process where non-stationarity is due to a trend is called a trend stationary process. In this case, we can have both stochastic and deterministic trend. The deterministic trend is because of the time trend, and the stochastic trend because of the this one, the stochastic one. If the root is equal to 1. Stationarity is a somewhat unrealistic situation in most of the macroeconomic variables. So a non-stationary process arises when one of the conditions for stationarity does not. So this we have already seen when we have a unit root, we have the non-stationarity problem. Such a process is also called a random walk. And in this case, since we do not have a constant, this is called a random walk without drift. A random walk without drift. Now, if we have a constant in this process, then it is called a random walk with drift. So it is called without or with drift because the presence of A will give a trend for the YT series. That is why the trend is called by drift. In this case, there is no trend. Therefore, this is a random walk without drift. Now, if we take the first difference of this one, YT equals YT minus 1 plus UT. Take the first difference, that is take YT minus YT minus 1. Then we will get delta YT. Delta YT is YT minus 1. And from this we find that that is equal to UT. That is the white noise, which is a stationary process. So delta YT now becomes a stationary process. So by differencing a random walk, we get a stationary process. So here, YT is made stationary through first difference. We have taken the first difference, YT minus 1. If we have higher order of log, then we can have higher order of difference. Now, since YT is made stationary through first differencing, this process, this random walk process with or without drift, or even with the drift, is called a difference stationary process or DSP. So we call a random walk or a non-stationary process different stationary process because we can make it stationary through difference. That is why it is called a difference stationary process. It is called an integrated process because from the differential series, we can come back to the original series through summation. So if we add YT minus 1 to delta YT, then we will get YT equals YT minus 1 plus UT. So that is the integration. So we can call the DSP process or the random walk also as an integrated process. So now remember, a non-stationary variable in time series we call as a random walk with or without drift. And it is also called a different stationary process or integrated process. Now, as I told you earlier, the process of inverse of differentiation is integration. So that is why this DSP is called an integrated process. Now, with one unit root, we can make YT a stationary through first difference. Only one time differencing is enough. Therefore, YT is integrated of order 1 and we write YT as I1. That is, there is one unit root. Now the different series, that is delta YT, it is a stationary series. For a stationary series, there is no unit root. That is, we have 0 unit root. Therefore, a stationary series we can write as integrated of order 0 and write it as I0. That means there is no unit root. So this is the usual notation that we use for the non-stationary series as integrated series of order 1 or 2 or 3 and so on. And if the order is 0, if it is I0, that means we have a stationary process. Now I2 means what? I2 means we have 2 unit roots in that particular system. The YT is integrated of order 2 with the 2 unit roots. So we write yt, we write like this, yt follows I1 or yt is an integrated process of order 1 and delta yt is an integrated process of order 0. So this is a notation that we use. Similarly, if a non-stationary series yt is transformed into a stationary one by differencing d times, that is delta d, okay, I am generalizing it. Then the series in level, that is the level variable, yt, we say is integrated of order d. That means there are d unit roots. So we write it as id. Yt is id. There are d unit roots. So that also means that delta d yt, that is we have difference to yt d times. So we have delta d yt. It is a stationary process I0. Now here I am giving 8 random ones starting at 0. So we have yt equals yt minus 1 plus ut depending upon the values of ut. We have 8 types of random walks. Now here we have the random walk in level and change. The level by t is given by this one. So this is the level variable. So the level variable is a non-stationary one. And the change, that is the difference 1, delta yt, is given as a stationary one. It is mean reverting process. So this is the change variable or the difference variable. So we have the level variable and the difference variable. So here also we have the same one. We have a level variable and the difference one. Now, whenever we have an integrated process of order D, then there is no tendency to return to 0. And that is given here. See, there is no tendency to return to 0. But I0, we find that it rarely drifts from 0. It will be always mean revert. It is always mean revert. So the ID may be taken as a quantum that is going away from the mean. And the other one, I0, our station process, is a mean reverter. Now, how do we identify whether we have a stationary series or a non-stationary series? And whether we have a stationary AR series or MA series or ARMA series and so on. For that purpose, in classical time series analysis, we use a graphical device called correlogram. This correlogram includes two types of representations. One is what is called autocorrelation function ACF. The other one is called partial autocorrelation function PACF. Now the ACF plots gives a bar chart of coefficients of the correlation, autocorrelation between a time series and its lagged values. And this explains how the present value yt of a given time series is correlated with the past, that is by t minus 1, by t minus 2 and so on, the past values. That means it is called a function because it is the correlations of a particular variable over the log k. That is why it is called a function. It's a function of the log k. For here I have used n. Now partial autocorrelation function those who know multiple regression knows the multiple regression coefficients are called partial regression coefficients. So the partial autocorrelation function represents actually it is the partial regression coefficient of our autocorrelation equation. Partial regression equation. So that means partial correlation coefficients between the series and its own lags are nothing but the regression coefficients or the partial regression coefficients of our regression function, auto regression function. So for example, for a first order AR process, that the beta, the root of the process, beta is both the autocorrelation function and the partial autocorrelation function. But when we come to the order 2, we have beta 1 and beta 2 coefficients. These are the partial autocorrelation functions. But using these partial autocorrelation functions, we have to find out the correlation function, the separate correlation function. Now, I shall give you the diagrammatic representation of these correlograms, ACF and PACF, for some process. Now, see, we know this is a stationary process. Actually, this is a white noise process. So, for a white noise process, what is the nature of the ACF and PACF? That is what we are going to find out. This time series plot I have taken in grade. So afternoon I shall show you how we get this. So this is the time series plot of a white noise process. Then what are the correlograms ACF and PACF of a white noise process? So here we have the ACF for the white noise process. Now you find two red lines here. These two red lines are the limits or the confidence interval. That is 95% confidence interval. This 95% confidence interval are given here, plus or minus 1.96 divided by square root of t. That is how we are getting the confidence interval, square root of t. T is the sample size. Now, if these are the autocorrelation coefficients, at lag 1 we have this one, lag 2 we have this one, lag 3 this one, lag 4, lag 5, lag 6, lag 7 and so on. And here we have the partial autocorrelation function. These are the partial autocorrelation functions, these values. And we find that for a white noise process, all the autocorrelation function and partial autocorrelation functions lie within the 95% confidence interval. So if we come across a correlogram where the correlation functions, both autocorrelation and partial autocorrelation functions, lie within or between the 95% confidence interval, then that particular series is a white noise series. So here we have the property of the white noise series in terms of the correlograms. Now I am taking another case. Here we have an auto-regressive process.
Excuse me, sir. Hello. Sir, I have a question, sir.
What is
Sir, actually, I tried using this ACF and PACF for determining the lags for my arts model. But the thing is that, sir,
ACF
like in your...
no, one thing. No, can you repeat it? Using the
Yes, sir. Actually,
ACF
I was
and
using a PACF for lag determination for my AR and MA model, RIMA model. So, like, whenever I try to use this model in a real-time data.
Sorry, somebody else also is speaking. Please, one at a time. Okay. Now, come on. Now come on.
Yes, sir. Actually, sir, what I'm saying is
Ah.
that when I tried this, making this ACF and PACF, this lag table with the real data, in your case, it was very circular, a very uniform up and down. It was very like a very uniform way. But whenever I tried on the real time data or maybe stock market data of like 5 years, 3 years daily data, the patterns are very different. So, how to determine the lag in that case?
You want to get the optimum lag or the otherwise? How
Sir,
many lags
actually,
you have to use?
basically, for my art modeling, for my arts and geometry modeling, I just want to determine what should be the, like in the mean equation, the ARIMA, what should be the lag for AR and MM.
In that case, you have to find out the optimum lag for fitting the model. Okay.
Yes, sir.
For
Yes, sir.
fitting the model. So see, in this case, the entire for example, this time series plot is for the entire period, and for the ACF and PACF, Gretel has taken by default. Gretel has taken by default. This is a monthly data. This is a monthly data. Therefore, Gretel has taken 2 years series. 2 years. That is 24 series as the lag. 24.
Yes, sir.
Okay. So, in most of the packages for graphical purpose, I think there may be a by default value. But for the estimation purpose, you have to give the optimum lag that you have to consider in modeling. The optimum there is in every package. I think there is a command for getting the optimum lag. So before modeling, you have to find out that optimum lag. For example, in the afternoon, I shall show you how we do it in grading. And usually this modeling is done in you are doing the war modeling thing, right?
Garch modeling. Garch modeling.
Arch model. Okay, so the in arch modeling, I think automatically it is the lag is considered automatic. The optimal lag is considered automatically in most of the packages. You need not give it. I think so. In EVs, at least it is like that. In Gretel also it is like that. You need not give the lag. The optimum lag is taken. But usually if you are doing the exponential gauge, then usually you are using only one lag. The model also will be fitted for one lag. Okay?
Okay, sir. Okay, sir. Thank you.
Yeah. Now this is the time series plot of an auto-regressive process. This is we know this is a stationary one because we have a large number of mean reversions. Now this is the ACF and PACF for the auto-regression. See, this is the first auto-correlation coefficient, second auto-correlation coefficient, third order autocorrelation coefficients. And we know these three are above the 95% confidence interval. So we say that we have significant spike for the first three lags. We have significant spike for the first three lags. But see the nature of these spikes. They are fast decaying. They are fast decaying. So for a stationary series, if the autocorrelation function shows fast decay, then we can assume that the given series is a stationary one. So this is a stationary series because we have the ACF with the fast decay. And now the PACF we will use along with the ACF for identifying whether we have an AR process or an MA process. Now here in PACF we find one significant spike. That means we have an AR1 process. And this is stationary. And here we have the order is 1. So we have a stationary AR1 process. That is the conclusion that we can make out of this. So for a stationary series, remember ACF will be fast decay. And PACF we will use along with the ACF to find the order of the AR. I'm not giving the MA process. MA process is the opposite of this. That is, if the PACF is fast decaying and we have a significant spike in ACF, then we can take it as an indication of MA1. So that is why I haven't given a place for MA process here. So for the MA process, we have the opposite of this. That is, for the PACF is fast decaying, and in ACF we have one significant spike for a stationary MA1 process. Now here, this is the time series plot of an ARMA process, AR-MA11. So this also is a stationary one. We have the ACF and PACF for the ARMA process here. Now remember, unfortunately, we know when we combine AR and MA process together, they will have the same properties of AR and MA, both AR and MA process. Therefore, it is very difficult to identify the order of the ARMA process from ACF and PACF. The only thing we can find out is whether it is stationary or not. If both are fast decaying, then our ARMA process is fast decaying, then our ARMA process is stationary. The order is not possible to determine. Even in the case of AR or MA process, actually, when we come to estimation, we have to do a lot of trial and error things, because getting at the correct value of a model, a time series model, ARMA model or ARIMA model is very difficult. We have to do a lot of trial and error. We have to estimate all the possible orders of AR, MA and ARMA. Then out of this, we will select one significant and adequate model depending upon last day I told you about the model selection, that is the information criteria. For which model we have the minimum information criterion that we will select out of all the significant and adequate models. So that is the ARIMA estimation procedure. I'm not giving it here. So this is for an integrated series. So evidently we do not have a large number of mean reversions. So evidently this is non-stationary. And the ACF and PACF for this non-stationary series is like this. The ACF is very slowly decaying. Actually, theoretically, the ACF must be equal to 1. ACF must be equal to 1. ACF must be equal to 1. But here, since we are using sample data, the sample formula has a particular differentiation. That means a particular pattern, and that is why the ACF shows a small decay. But now here, let us see, even after 24 log, the ACF is not decaying. That is, it is not coming to 0. That is an indication of non-stationary. So if the ACF is slow decaying, then it is an indication of non-stationary. The PACF will usually tell us the order of the non-stationarity, whether we have 1 or 2 or 3 unit roots, but it need not be actually theoretically it should be like that, but for the sample data it may not be like that. Actually, in the data that I have given, there is only 1 unique root, so we should have only one significant spike, but here it appears that we have two. It so happens with the sample data. Now this is a stationary arch process, the time series plot, and this is the ACF and PACF for the arch series. Now see, it can so happen that sometimes a later lagged value may cross the 95% confidence interval. Sometimes it can so happen, but even then we can take it as stationary one. This is a later one. Now let us compare the integrated processes I1 and I0. As we have already seen, I1 series vantages widely. That is I0. On the other hand, the I0 series is mean reverting. So there may be direct or oscillatory convergence to the mean. Then I1 series has infinitely long memory of its past behavior. That is, we have already seen that the I1 series has a stochastic trend. That stochastic trend is the sum of or the accumulation of all the past random shocks. U1 plus U2 plus U3 plus and so on. All the past shocks, or UT plus UT minus 1 plus UT minus 3 plus and so on. So we say that it has infinitely long memory of its past behavior. That is, the shocks are persisting. We have the persistence problem. And this is even from the very slow decay of ACF. That is sample ACF. Okay. Theoretically, there is no decay at all. All the PACF will be equal to 1. ACF also will be equal to 1. Now, I0 series has a limited memory only because the shock effects are only transited. For the particular process, we have only one time shock, UT. And this is evident from the fast decay of the autocorrelation function. Now, this is the WPI all commodities in level variable. And if we take the first difference, we have a plot like something like this. And if we take the second difference, then we get a large number of mean reversions. That is an indication. That may be an indication that WPI includes. Can you tell me how many unit roots? Anybody?
The 2-unit roots, sir.
Yeah. Possibly we will have 2 unit roots. Because the first difference is like this. We have only very few mean reversions. Anyway, remember the parallelogram or this time series plot need not tell us the true picture. Okay, to some extent the parallelogram will, but not the time series plot. So we have to go for either to some extent the parallelogram, and then definitely we have to go for the unit root test to find out how many unit roots we have. Now coming back to the trend stationary process, TSP. So we have we can write a deterministic trend like this. Yt equals A plus Bt plus Ut. So this A plus Bt will give us the deterministic trend. Here Ut is a white noise process. We call this a trend stationary process because we have stationary fluctuations around this linear trend. A plus Bt is the linear trend. Now, for a non-stationary process, we know the mean changes with the time. So if we take the expectation of this series, that is, if we take the mean of this series, we can find that this is equal to a plus bt, because expectation of ut, the mean of ut is 0. So we get the mean of the trend stationary process as a plus bt. It is the expected, the mean is changing with time. It's a function of time. But if we take the variance and constant one covariance of this deterministic trend, this TSP, we can find that both are constant. That is sigma v squared. The covariance is only a function of the lags, k only, not a function of time. So a TSP, trend stationary process like this, is it has a constant variance and a constant or independent variance and independent covariance. Both are independent of time, but the mean is a function of time. But we can, since this is a function, this mean is a function of time, we can use this expectation of yt or the regression of yt in terms of the estimated values of a and b, a hat plus b hat t, for forecasting purpose. Forecasting the recent future only, not for a long time period, for a long future horizon. No, for a limited period of future periods, we can have the mean value of this one. Now, remember the trend stationary process and the difference stationary process. For the difference stationary process with a constant, all the characteristics, mean, variance, and covariance are all functions of time. But for a trend stationary process, variance and covariance are independent of time. That is, the covariance stationarity is met. The only problem is with the mean. Mean is a function of time. But if we do not have a constant, if we do not have a constant, then also we will have the mean in terms of the trend. So remember the difference between TSP and DSP. Now, how can we make a trend stationary process stationary? Now, do you remember the difference stationary process? We make stationary by differencing it. So the trend stationary process we can make stationary by removing the trend or detrending it. So we have the trend given in terms of expectation of yt. So if we go back here, expectation of yt is a plus bt. So if we remove this a plus bt out of this yt, then yt minus expectation of yt will be equal to this ut, which is stationary. So that is the process of detrending, yt minus a plus bt. So we are removing the trend, detrending. So we can make TSP stationary by removing the trend, that is detrending. Now in a regression framework, how do we detrend a series? Can anybody tell me? In a regression framework, how can we detrend it? Suppose we have a TSP in terms of some other variables. All the variable, say yt and xt, both are TSP, and we want to make both TSP, that is trend stationary process, that is making it stationary. How can we make it stationary without doing manually or in Excel or otherwise, without subtracting that particular trend? Is there any method for detrending in the context of regression analysis? Anybody?
So first difference or taking log.
Taking the log. No. That will not detrend. That will give us some something called something uniformity. That is it.
Yes.
That is, it will reduce the variability
Yes.
in the values of variables. Variability. It will not detrend. Anybody else?
First difference, it looks the difference. Only option I look, it looks first difference or second difference with the augmented Dickey-Fuller test.
No. Little louder.
Sir, I was
What
saying
is
the
it?
first difference with the help of augmented Dickey-Fuller test.
So first to do the Dickey-Fuller unit root test. No, for a TSP we need not do the Dickey-Fuller unit root test.
Okay.
Because it is not a difference stationary process. For a difference stationary process only we need to do the unit root test. For a TSP there is no unit root. There is only a trend. How can we detrend it? How can we remove the trend? Usually we do the detrending like this. That is, we first estimate the A plus BT, get the estimated value, then that estimated value we will subtract from YT. YT minus A plus BT. Then the remainder, the residual will be a detrended stationary value. So instead of doing this detrending directly like this, suppose we have two TSP variables, trend stationary process variables, that is YT and XT. Okay, both are trend stationary process, and we have a regression equation YT as a function of XT. So we regress YT on XT. The problem is both the variables are TSP, and there is a trend in both YT and XT. So the regression coefficients, the estimates, will not be free from that trend. That is, we will not get the true value of effect of XT on YT. That we will get after removing the trend from YT and XT, and then doing the regression with the detrended values of YT and XT. That is, we do a regression of detrended YT on detrended XT. Then we will get the pure effect of XT on YT. But that is a cumbersome process. We have to do several times. First we do a regression of YT on time. Get the trend. Then subtract this trend from YT. Then we do another regression of XT on time. Get its trend. Remove that trend and get the residual from XT. So the two residuals are detrended values. Then we do the regression with the residuals, the detrended values. It's a cumbersome work. It will take a lot of time. But actually in multiple regression, we have a method for detrending such cases. And that is the beauty of multiple regression. Multiple regression does it automatically. That is, if we do a multiple regression of YT or XT and time, we include a time variable explicitly in the regression. Then there is a theorem called the Frisch-Vogel theorem. According to Frisch-Vogel theorem, if we include a time variable, a trend variable in a multiple regression framework, then the presence of the time will detrend automatically all other variables in the regression. So the partial regression coefficient of that xt will be the true effect of xt on yt. That is the effect of detrended xt on detrended yt. So remember that if we have a DSP, all the variables are having, or some of the variables in our multiple regression are having a trend. We need not go for first to detrending and then doing all the regression. We just include a time variable in the regression, in the multiple regression. That the presence of that trend will automatically detrend all the variables. And that is the beauty of this Frisch-Borg theorem. Okay. So in general, we are detrending a variable like this. And now this yt minus expectation of yt will be a stationary variable. So here we have a TSP. See, remember there is a trend like this. The trend is equal to 1.5 plus 0.5 t. And here we have the detrended series. So once we have removed the trend, we get an almost stationary series.